When you think about ceramics, like ancient pottery that's lasted for thousands of years, or even just the tiles in your kitchen, you think of permanence, right? They don't rust or rot away. But what if I told you that their greatest strength, their amazing chemical stability, is also, well, it's the secret to how they can be destroyed. It's a hidden battle, and we're going to dive right in.
So that's really the big question we're tackling here. Are these materials truly forever? I mean, we see them survive fire, we see them last through the ages, but it turns out that with the right conditions, even the strongest ceramic can be taken apart.
And the key thing to get your head around is that this isn't corrosion like the rust you'd see on a car. That's a whole different process. With metals, you've got these electrochemical reactions going on. It's like tiny little batteries all over the surface, powered by water and oxygen. But ceramics? No, they fall victim to something way more sneaky, a direct chemical attack. We're talking about acids or bases that just dissolve them molecule by molecule. It's slow and totally invisible.
All right, so this brings us to what I think is a fascinating paradox, the myth of their invincibility. It's kind of wild, but their incredible stability, the very thing that makes them so tough, is also the secret to figuring out how they can fail.
There's this really cool idea in material science, and it sounds kind of strange at first, but check this out. You can think of ceramics as having already been corroded. I know, weird, right? But it actually makes total sense. See, most ceramics are oxides. That's a metal combined with oxygen. And what's rust? It's just iron oxide. So a ceramic is already in that stable, final form that a piece of metal is trying to corrode into. That's exactly why they're so stable to begin with.
Okay, so let's break down this tale of two corrosions. With metals, like we said, it's an electrochemical thing. You need water, you need oxygen, and boom, you get rust and pitting. But for ceramics, it's a totally different ballgame. It's a chemical dissolution process. They're vulnerable to acids and bases, and the result isn't rust, it's things like leaching, or the surface losing its shine and going all matte.
So how does this invisible attack actually happen? Well, it really comes down to two main strategies. Two different ways chemicals can go after a ceramic surface. First up, we've got something called leaching. You can also call it ion exchange. The best way to think about it is like a chemical trade. Imagine an acidic solution comes along and says, hey, I've got these hydrogen ions. The glaze on the ceramic basically says, cool, I'll trade you for my weaker ions, like sodium. This little swap creates a new altered surface layer, and that layer is much, much weaker. The second type of attack is even more brutal. It's called matrix dissolution, and this is a much more direct assault. Here, the environment is so harsh, think a strong acid or alkali, that it doesn't bother trading. It just starts breaking down and dissolving the main structural network of the material. It's literally like dissolving the skeleton that holds the whole thing together.
And we actually have a really good model for how this goes down, believe it or not, from research into storing nuclear waste. It's a three-stage process. First, water gets into the surface, and those weaker alkali ions, like sodium, start to leach out. Now here's the kicker. That actually makes the water right at the surface more alkaline. And what did we just learn about alkalis? They attack the structure. So in stage 2, that now alkaline solution starts dissolving the main silica network. Finally, in stage 3, some of that dissolved stuff can fall back onto the surface and form a new layer. Sometimes this can slow things down, which is good, but the damage is already underway.
But look, the chemistry is only half the battle. Think of it like this. For an army to take a castle, they need a way in, right? A crack in the wall, an open gate. It's the same thing here. The corrosive chemicals need a path to get inside. And that's where the physical structure of the ceramic becomes absolutely critical. Tiny, invisible flaws can become superhighways for corrosion. Just look at this diagram. A glaze can look perfectly smooth and shiny, totally impenetrable to the naked eye. But zoom in, and it can be riddled with micro cracks. Every single one of those cracks is a little highway, a direct channel for corrosive stuff to just bypass the protective glaze and go straight for the weaker ceramic body underneath.
And it's not just cracks either. There are all sorts of weak points in the armor. You've got porosity, which are just tiny connected holes. You've got the grain boundaries, the places where the individual crystals meet up. You can even have unbonded areas or pinholes. Basically, all these little imperfections, many of which are just a normal part of how ceramics are made, become the perfect starting points for corrosion to take hold and spread.
So the key takeaway here, the big thing to remember, is that corrosion is controlled by two things: chemistry, the actual reaction, and transport, the pathways that let the attack happen. It's a 1-2 punch. You need both the right chemical weakness and a physical path for the bad stuff to get in.
You can't have one without the other for corrosion to really take off.
Okay, so if we know how these things fail, the next logical question is, how do we fight back? How do we stop it? Well, the first step is always testing. Scientists and engineers have come up with a whole arsenal of tests to simulate these chemical attacks and figure out exactly where a material's breaking point is.
And let me tell you, in some cases the stakes are unbelievably high. What you're looking at here is a refractory, a special kind of ceramic pouring molten metal. This thing has to survive not just mind-boggling heat, but a constant, brutal chemical attack from the molten metal and slag. If this fails, it's not a little crack, it's a catastrophe.
So there are all kinds of tests to simulate these different conditions. For example, to test for alkali attack, maybe something you'd find in a furnace, they'll literally hang a sample over some heated alkali salts. For something like the glaze on your dinner plate, they'll soak it in acetic acid, which is pretty similar to vinegar, to make sure nothing dangerous like lead is leaching out. And for tiles, it can be as simple as putting different staining agents on them to see how well they can be cleaned. But of course, there's always a catch. A lab test is great, but it can never perfectly replicate the messy, complex conditions of the real world.
All right, that brings us to the most important part of this whole story, the solution. Now that we understand how ceramics are attacked and how we can test for it, we can get smart. We can actually design them to be more durable.
And the goal is really to build a stronger, more stable chemical structure. The best way to think of it is like building with Legos. The glass network in a glaze is a bit like that. A bad design has a bunch of bricks that are barely connected, really easy to pull apart. A good, durable design creates a network that's highly interconnected, stable, and polymerized. Basically, a structure that's really, really tough to dismantle. And this chart really lays it out. On the bad side, a vulnerable design has tons of those free alkalis, like sodium and potassium. Those are the weak links, the ones that get traded away so easily. On the good side, you minimize those. Instead, you pack it with strong network formers like silica and alumina. Those are the Lego bricks that lock everything together tightly. And of course, on top of the chemistry, you have to get the physical structure right. A good design has a flawless surface, with no pinholes or microcracks for the enemy to get in.
And the science is absolutely crystal clear on this. The research shows that the more of those alkali ions you have in your glaze, the faster they're going to get released when something attacks it. It's that simple. So managing those weak links, the alkalis, is probably the single most important thing you can do to design for durability.
So for an engineer, the playbook is pretty clear. Here are the key actions. First, you want to increase your network formers. Add more of the strong stuff, like silica and alumina. Second, you have to control the modifiers, those soluble alkalis. Get them out or lock them down. Third, you work on the matrix itself, making it denser and better bonded. And finally, you perfect the surface. Get rid of those pinholes and cracks. You have to tackle both the chemistry and the physical structure to win.
It's pretty amazing when you step back and think about it. For most of human history, we just built things and hoped for the best. We hoped they would last. But now, we can understand how they fail, right down to the molecular level, which means we can actually design them for real long-term permanence. So it leaves us with this incredible question. Now that we can engineer materials to resist decay on a chemical level, what truly permanent structures are we going to build next? What are the limits?